Hi, in this video, I'll be going through what is a multi-stage game, and I'll talk specifically on what happens if this multi-stage game becomes infinite. So, a repeater game is just a dynamic game in which the same stage game is played at every stage. We have already seen this example in the previous game where we have a two-stage game. But let's expand on that idea and have a multi-stage game. So after every stage, players observe the actions by the before players and make their own choice based on it. The repeater game has either a finite or infinite number of repetitions. And let's take that example of the prisoner's dilemma, but it's repeated twice. We can see that in the first prisoner's dilemma, four is there'll be in the first prisoner's dilemma, in this repeated prisoner's dilemma, the SPNE will be taking CC in stage 2 and CC in stage 1. Why? Because CC is the Nash equilibrium for this game, even if it's repeated twice. And so, the proposition is that if the stage game has a unique Nash equilibrium, then the finitely many repeated game has a unique SPNE, which will then be the Nash equilibrium at every stage game. And the proof follows from backwards induction. For example, if you take this as your stage 2 first, then, or stage 3, then the player in that game in stage 3 will play 1-1. If you go back, there's no effect, so you'll play 1-1 again. And then if you go back one more time, you see that it'll play 1-1 one more time. So in all the stages, it'll play the same SPNE. It will play the same Nash equilibrium. So when you combine them all, that will be the unique subgame perfect Nash equilibrium. And now we take a look at an example where we modify the prisoner's dilemma game to have 3 prisoners now. So we have 2 prisoners, but each prisoner has 3 choices. And in this game, where we draw this matrix, this will be the playoff matrix. In this game now, we have 2 NEs. So CC is 1 and AA is also 1. And if you repeat the game, there will be a SPNE that actually plays DD in the first stage. So the reason is this: if you play AA if you play DD, then you get to play an AA in the second stage. And if you don't play DD, then you play CC in the first stage. So if the strategy, so why is this so? Well, we just need to take game 1, add with game 2, because that's how the payoff is created. So when you add them together, this will be the final matrix. And we actually see in this case now, there will be 3 pure strategy Nash equilibrium: DD, CC, and AA. And each of these will then correspond to the SPNE of the 2-stage game: CC, CC, AA, CC, DD, AA. So I hope that's quite clear on how do you get this. And we'll move on. So in this example, in the previous example, we now show that how credible threats have an influence on the current's behavior, and this allows for negotiation among the players. Because we know that in stage 1 now, we don't need to play always CC, and we can choose other outcomes. So, but however, in the two-stage game, the game perfect equilibrium outcome, DDAA, may not be strong enough in credibility. So you see, if you after reaching stage 2, players may have an incentive to play AA instead of CC, regardless of what happened in stage 1. And if the players anticipate this, then they can deviate from DD in stage 1. But as the periods of repetition increase, meaning you keep repeating the game, then the credibility will increase. So how do we understand this mathematically? Is that, let's say, we assume that the players discount the future returns with a common ratio delta. And this is the payoff obtained for each period. Then the present value of this infinite sequence of payoff will be pi 1 plus delta times pi 2 plus delta squared times pi 3 all the way. And you can form the geometric series to form this. Then the average payoff, so you can combine them to look like this summation. Then if there is some average payoff 5, so that means 5 plus delta 5 will just equal to this. Then this thing is geometric series, so it's 5 over 1 over delta, 1 minus delta. Then you cross multiply, it means that the average payoff is this function. And if we do consider the infinitely repeated prisoner's dilemma game, then there will be a SPNE in which both players play the non-cooperative strategy CC, because obviously CC is a Nash equilibrium. But there can also be a cooperative strategy if this delta is big enough or close to 1. Why? Let's say delta is close to 1. The understanding is that this now become very small. So the payoff is actually very little in this game. So instead we can deviate from that and choose some other strategy, and this is known as the trigger strategy. So for example, play D in the first stage. So your first stage, instead of choosing CC, you play D somehow. In the T stage, if the outcome of all the previous stages is DD, then you continue playing D. Otherwise, you play your Nash equilibrium C. If you adopt this, both players will adopt this trigger strategy, then the cooperative outcome DD occurs in every stage. So the claim is that we will adopt this trigger strategy if and only if the discount factor is larger or equals to 1/4. Reason, let's assume that player I adopts the strategy and we will find the best response from J. The case 1 is that the previous stages is not DD. Then I will then play C based on this trigger strategy. Then player J, best response is also play C forever. And in the case 2, let's say all the outcomes are DD. Then if J deviates from playing C at this stage, then the deviation, so all of them DD. If now player J, let's say player 2 changes to C, he gets 5 units in this stage. But then we'll trigger C from player J in the next stage onwards. So it is 5 plus 1. So because once you choose C here, the next player will choose C already. So it will always go back to 1. So it's 1 plus 1 times delta, 1 times delta square all the way. So it's 1 plus delta over 1 minus delta, 5 plus delta over 1 minus delta. And if J were to keep to this trigger strategy, then the total payoff should be this. Because J will always have 4 then therefore playing the trigger strategy is optimal. If and only if, so this is the trigger strategy. This is what happens if you deviate, and this is what happens when you stick to the trigger strategy. So this thing needs to be greater than this. So in that case, we reduce it to form that delta must be larger or equals to 1/4. And we can further understand this by the Fuchs theorem, but we won't prove Fuchs theorem, is that if this is the payoff for the Nash equilibrium of stage game G, and x1 x to xn is the payoff for any other feasible choice, for a sufficiently close delta, there will always exist a sub-game perfect Nash equilibrium that achieves this payoff that you want as an average payoff. So understanding that is that, okay, so let's say we have the Connaught duopoly game again, and these are the outcomes. Then we can consider this trigger strategy for the game now, where we produce half the monopoly's quantity in the first period, and in the 10th period we produce Q at, we stick to this quantity if both firm produces it in all the producing one. But if one of them deviates, then we'll go to QC forever, which is the Connaught quantity. So in that case, now we suppose that I adopts the trigger strategy for J at some period T. Then to the collision playoff, meaning when they become one monopoly, will be this outcome. But if you deviate from this strategy, then you first produce PD, whichever what's your payoff from not producing QM over 2, then all the others will then become QC forever. So it's become PC this Connaught's equilibrium profit. In that case now, this will be your average pay, your overall payoff. And if both players were to play the trigger strategy, that means we stick with this. This has to be greater than this. And so you just do this comparison method, and we see the delta must be larger or equal to 9/17. So we can see when in this case we'll adopt this trigger strategy to produce this payoff. So I've come to the end of this video. If you have any questions, you can leave it in the comment sections, or you can rewatch the videos multiple times to understand it. I'll catch you in the next one. So see you. Bye.